And a complete graph is what? A simple graph in which there is an edge between every pair of vertices. And you should know the difference between complete graph and connected graph. For connected graph, we said there is a path between every pair of vertices. So there is a difference between path and direct edge. And Kn is used to represent complete graph. And for a simple graph, it is always true that 2 times the number of edges is always less than or equal to n square minus n. Or we can just put it like this. So 2 times number of edges is always less than or equal to, so nc2. That is choosing 2 vertices at a time out of n vertices and drawing an edge between them. And for a complete graph, so these two numbers are exactly same. So m is equal to nc2. The number of edges is directly equal to nc2. If this condition is satisfied, we can construct a complete graph with that data. If this condition is satisfied, we can in this case we can construct a simple graph with this data. If this condition is satisfied, we can have a complete graph itself. And if you come to walk, trail, path, circuit and cycle. So walk is something which is casual. Here there is no restriction, like you can just move on any edge, any vertex, any number of times. So only thing is, if I'm saying like it is AD walk, if I just say it's an AD walk, which means that the walk should start at A, end at D. Okay, so how many times you moved on a particular vertex or particular edge in this walk, it doesn't make any difference. It's just like morning casual walk, what people may do. And open refers to what? The end vertices are different. Closed means end vertices are same. So trail is an open walk. Okay, trail is open walk in which no edge is repeated. You can have the repetition of vertex. You can. So it is not something which is must. You can have the repetition of vertex. For circuit, it's a closed walk. So there is no repetition of edge, but you can definitely repeat vertex, but it is not something which is completion again. But for a path, there is no repetition of vertex. You should know that if there is no repetition of vertex, obviously there is no repetition of edge as well. And cycle is nothing but closed walk in which there is no repetition of vertex. So as usual, there is no repetition of edge as well. Normally problem on this are important. And as I mentioned, connected graph is nothing but what? A graph in which there is a path between every pair of vertices. So distance refers to what? You can have more than one path between two vertices. So for example, in this case itself, if I want to reach H from C, so 1, 2, this is one path. So 1, 2, 3, this is the second path. Out of these two paths, so you can note that this is the shortest path. So the length of the shortest path refers to the distance. Length always refers to the number of edges we are using to traverse from one point to another point. And complement of a simple graph just says what? If you have a complete graph of, if you have a simple graph of n vertices, then consider a complete graph with n vertices, then delete the edges which are present in G in complete graph. That will give us the resulting complement. And so these problems are quite important. And on bipartite graph, the problems are important again, and this theorem, as I mentioned, this theorem is once again very important from the point of your examination. And on complete bipartite graph, you can expect the questions. Yeah, so now we were discussing vertex degree. So on vertex degree, so what I said, so the number of edges incident on the vertex V gives degree of the vertex, and if there is a loop incident on the vertex, then that loop gives a contribution of 2 to the degree of the vertex. Okay, gives the contribution of degree 2 to the degree of the vertex. But if I am counting the edge, it is counted only once. So this is one edge, but this is giving the contribution of 2 to the degree of this G. And afterwards we noted few things. So this vertex F, sometimes they can ask you like this. So after from this one, show that handshaking property is satisfied. Identify the isolated vertex, pendant edge in the graph. So pendant vertex refers to what? The vertex with the degree 1. Isolated vertex means vertex with the degree 0. Pendant edge means an edge which incidents on the pendant vertex. And what the handshaking property says, sum of the degrees of all the vertices is always equal to 2 times the number of edges. Okay, so you can just expect this question in the exam, like they can ask you to verify this handshaking property. So why we are giving a name to it as handshaking property? That's the next question. We are calling it as handshaking property because okay, it is like see, the two people are here. So let me assume that D is one person, F is another person. So if they do handshake, D says I made one handshake, F also says he made one handshake. But actually for the person for the third person who is seeing, who is looking at it, for him only one handshake happened. But he made one handshake and he made another handshake. So which means that with respect to these individual persons, the number of handshakes happened is 2. If I ask him whether he made the handshake, yes, he says 1. And even this person is saying 1. So which means that both the person has given the contribution to the handshaking. But for the third person who is looking at this handshake, he says that only one handshake happened. So that's what. The one handshake what happened, this is the edge. And these two persons are saying that I made one handshake and I did one handshake. So what these two people are telling, so that is giving the contribution to the degree. Okay, that's why this it has taken the name handshaking property. Okay, so I told you that the proof of this one is also important, and we are using this result very often for almost every result from now onwards, whatever we are discussing. So this result is used. Okay, now let me see a next theorem. It's very important, and I told you that it's part of your model question paper as well. And this is what this theorem says. It says that in any graph, okay, it's a general graph, it's a general arbitrary graph. If you can see any arbitrary graph, just a minute. Yeah, so in any graph G, the number of vertices are 40 degree. Wait a minute, so there is some issue with this. Okay, right, we can just continue. So in any graph G, the number of vertices are 40 degree. The number of vertices 40 degree is always even. Okay, so please try to understand this. Number of vertices of odd degree is always even. So as I mentioned, they can ask you to prove this result, and that can be seen even in this example. This is some arbitrary graph I have chosen. It has got multiple edge in it, it has got loop in it, pendant vertex, isolated vertex. Just consider a general graph which can have all the possibility. And you can note that the number of vertices of 40 degree is only 2. And this is what this one is saying. It need not be 2, but it cannot be in odd number. So number of vertices of 40 degree is always even number. Okay, let me just prove this result. Okay, so they're saying that G is some G is an arbitrary G is some arbitrary graph. Okay, let me assume that in this graph G, that G is equal to V comma E. GB made up of this vertex set and this edge set. And let me assume that this graph has got n vertices in it. Let me assume out of which, so V1, V2, V3 and so on, Vk be odd degree vertices. what I'm doing here, I have n vertices. I'm assuming that out of these n vertices, the first k vertices are of odd degree. Okay, now which implies that, which obviously says that the remaining vertices, that is vk plus 1, vk plus 2, and so on vn, these are all are even degree vertices. Okay, in this, let me just try to understand what we are supposed to prove in this. What I am supposed to prove? Number of vertices of odd degree is even, which means that we just need to prove that this k, okay, this k whatever is written here, I just need to show that this k is, okay, I'm sorry. Okay, I just need to show this k is even number. That's what the role here is. It is to prove that k is even. It is nothing more than this. Okay, now how to show this? So for this one, I'm just directly taking the help of the handshaking property. Okay, let me just see what handshaking property says. We know that handshaking property says that, since this is a graph, this is some arbitrary graph G, handshaking property holds good. And what the handshaking property says, summation I is equal to 1 to n degree of vi. Okay, so summation I is equal to 1 to n degree of vi, which means degree of v1 plus degree of v2 plus degree of v3 and so on up to degree of vn. So this sum is equal to 2 times the number of edges. And what we know is this number is always what? Even number. So this is even number. Okay, now let me just rewrite this summation. I can just rewrite this summation as summation I is equal to 1 to k degree of vi plus summation I is equal to k plus 1 to n degree of vi is equal to even number. Okay, now just have a look at this one. This is what? Degree of v1 plus degree of v2, degree of v3 and so on. And what we said, these numbers are what? Even numbers. These are all even numbers. Which means what this number is. So this number becomes what? Even number. So that says that summation I is equal to 1 to k degree of vi is equal to what? Even number minus even number. What does it gives? It gives an even number. Please try to understand. So this is sum of even numbers like degree of vk plus 1, okay, degree of vk plus 2, degree of vk plus 3 and so on, degree of vn. These are all what? Even number. This may be 2, this may be 4, this may be 8, this may be 4 again. These are all even numbers. If I'm adding these even numbers, I'm supposed to end up with what? An even number. That's what I'm telling. This is nothing but this summation gives us an even number, and this RHS is even, and definitely this number is bigger than this number. And when I subtract this one, it's an even number. It need not be a negative even number. It will be a positive even number. Now, this summation is equal to even, and what we know is, okay, what we know is if we just add two even numbers, two odd numbers. So 3 plus 3 even number. If I consider 3 plus 5 even number, which means that 3 plus 5 plus 3, this becomes what? Odd number. Which means that if we are adding even numbers, that is odd number of even numbers, sorry, odd number of odd numbers. If we are adding odd number of 1, 2, 3, odd number of odd numbers, we are going to end up with what? Odd number. And if we are adding even number of odd numbers, even number, that is 2 number here. So even number of odd numbers, we are going to end up with even number. Now have a look at this one. This is saying what? Degree of v1 plus degree of v2 plus degree of v3 and so on, degree of vk. If we have got odd number of, if this k is odd, we are adding odd number of odd numbers. Okay, the sum is we are just counting odd numbers. How many times? Odd number of times. As a result, I am supposed to end up with what? Odd number. But we are saying that this summation should be an even number, and this summation becomes even provided your k itself is even number. That's all. I hope you people understand this. That is, so this is degree of v1 plus degree of v2, degree of v3 plus degree of v4, and so on, degree of vk. Let me assume that this is degree of v1, degree of v2, degree of v3. If I am adding these three numbers, all are odd numbers, so definitely I am going to end up with the sum is what? Odd number. If I am adding these two odd numbers, I am going to end up with even number. So which means that, so this k should be what? Even number. That's all. It's very simple. Please try to understand what I did here. I first assumed that the graph has got n vertices. Then I went with an assumption that out of these n vertices, k vertices are of odd degree and remaining vertices are of even degree. So there is no issue when we are adding the even numbers. Sum of even numbers is always even. So it is how many even numbers are there here, whether we have got 2 even numbers or 10 even numbers, doesn't make any difference, or 3 even numbers, doesn't make any difference. But when we are adding odd numbers, so it depends whether this sum may be an odd number or even number. If k is odd, this becomes odd. If k is even, this sum is also becomes even. So since we are expecting the summation should be an even number, okay, we are saying that the summation should be an even number, and that is possible only when if k itself is even number. Okay, so this theorem very important from the point of your examination. Make sure you are reading this, and as I mentioned, the proof part is so simple, so please practice it. If anybody has doubts, we can discuss. Okay, now next question is, this is one more possible question under this heading with respect to the whatever we learned just now. Okay, the question is, determine whether the graphs with following degree sequence possible. Okay, question number 1 is what the given degree sequence is: 1, 1, 3, 5. So what they are saying here, the problem is saying that you have got 4 vertices, 1, 2, 3 and 4 vertices, and degree of the vertex 1 is 1, second vertex degree is 1, third vertex degree is 3, and fourth vertex degree is 5. So can we have this graph? Yes, it is possible, because we have got even number of odd degree vertices here. Okay, it is possible by using the theorem on by just stating this theorem. Just by stating this theorem, you can just conclude that it is possible. Let me consider this example. It's 1, 2, 3, 4, and even this one is possible because we are saying that we have got 2 vertices of odd degree. But if I consider this one, it is not possible. If you want, I can just try to construct this. It's just impossible. Okay, it's just impossible to construct this graph. I will show you. I will just show you how it works. Okay, let me assume that this is the degree of A, this is degree of B, this is degree of C, this is degree of D, and this is degree of E. Okay, now A, B, C, D, E. Let me try to maintain its degree. So we are saying that E has got the degree 5. So which means 1, 2, 3, 4. What about 5? So to make the degree of this one 5, I cannot have the loop because that loop will give the contribution of 2. I can have the multiple edge here because I need to have multiple edge, no other option. Okay, if I draw the multiple edge, so it should be, I can go up to C. Okay, let me do that. So degree of E become 5, it's satisfied. Degree of E is already done. So E is done. Now degree of C is 3. So degree of C became 2 now. And just to make the match, so I will just draw this edge so that the degree of this one also matched, which is 3. Degree of B is 2, even that is done, and degree of D is what? 4. Now where to map this D now? So degree of D should be 4, but degree of E, A, B, C is done. I cannot connect this to any of these vertices. Only option is what? Having a loop. Suppose if I consider one loop, what happens to the degree of this one? So 1, 2, 3. I need to have one more degree for this. I need to include one more degree, which means that I need to have one more edge. And if I'm drawing an edge, it cannot be a loop now. I'm supposed to draw an edge which incidents on 2 vertices. But these are the only 5 vertices we have, and we can note that for these 4 vertices, the number of degrees already taken care. So which means we can note that we just cannot find the we cannot match the degree of this D. So that is where it failed. But if you just remove this D, or if you remove this D, it's of no use. If you just remove either E or C or A from this, you can note that you can definitely have the graph with the degree sequence. I think people are clear with this, and let me talk about the next set of problems. So as I mentioned, problems on degree is very, very important. From the point of your examination, 100%, sometimes you people can definitely see question papers of this kind as well. That is, if you just the question paper carrying only problem on vertex degree and isomorphism. So these two concepts are very, very important. Out of these two, at least one will be there in the question paper. Sometimes both will be there in the question paper. Okay, but normally one subdivision will be definitely there on isomorphism. Okay. Okay, so before getting into more problems on vertex degree, I just wanted to give one more definition called regular graph. Okay, and this is what it says. Okay, a graph in which all the vertices are of same degree. That's all. Same degree, K is called K regular graph. It's called K regular graph. And you should keep one thing in mind. When I say K regular graph, the graph is not something which is unique. So that can be you can have that K regular graph in different shapes. For example, let me consider a few examples here. Okay, let me assume that I just want. Okay, so examples of 2 regular graphs. 2 regular graph. 2 regular graph means degree of each vertex is 2. Okay, now look at this one. Degree is 2, 2, 2, 2. You can have this. Degree is 2, 2, 2, 2, 2. So you can have them in different shapes. Degrees 2, 2, 2. When I say 2 regular graph, it is not something which is unique. You should keep that in mind. You can have that in different shapes. And 3 regular graph means degree of each vertex is 3. Okay, so and example. Okay, let me just see a few examples on that one as well. Examples of 3 regular graphs, and these are not the only set. You can increase this. So I just showed you that. So if I just say 2 regular graph, it is not something which is unique. You can have it in different shapes. That's what I just wanted to tell you through that example. Okay. Degree is 3, degree is 3. Now degree of these 2 vertices became 3. So 3, 3, 3 and 3, and there is no vertices here. Okay, only these vertices are there. This is A, B, C and D. These are the 4 vertices we have, and degree of each vertex is 3 in this case. Okay, if I consider one more example, let me consider this, and this is called Peterson graph. And do we have story? Okay, note that here degree of each vertex is 3. Okay, it's A, this is A, this is B, this is C, D, E, F, G, H, I, J. You know the degree of each vertex is 3 here. So this is one more example of 3 regular graph. These are not the only 2 examples, you can just find some more. And 3 regular graphs are also called as cubic graphs. If we say cubic graph, so we are referring to the 3 regular graph. Okay. The most, as I mentioned, so the most common question on degree of the vertex is this. They may ask you to find the degrees, they may ask you to find us the number of vertices or number of edges in the given situation. Right now, this is what the problem is. Determine, so cardinality of V for the graph G is equal to V comma E if, case number 1, G has 9 edges and all vertices have degree 3. And question number 2, G has 10 edges with 2 vertices of degree 4 and remaining vertices are of degree 3. And C, G is regular with 15 edges. Okay, this is also this is the most common question in the previous year question papers as well. Let me just check out this. And as usual, we will directly take the help of handshaking property in all these cases. Here in each of the problem, I need to find cardinality of V. So let me just check out the first one. So they are saying that, so we have got the number of edges is equal to 9 and all vertices of degree 3. So they are saying that degree of Vi is equal to, so degree of Vi is equal to okay, so degree of Vi is equal to 3 for I lying between 1 and n. Let me assume that we have got n vertices here, and let me just compute that value of n. Okay, what the handshaking property says, sum of the degrees equal to 1 to n, degree of Vi is equal to, so 2 times the number of edges. So what we know is we have got n vertices and degree of each vertex is 3. It is like this is nothing but degree of V1 plus degree of V2 plus degree of V3 and so on plus degree of Vn. This is 3 plus 3 plus 3 plus 3 plus, you are just adding 3 to itself how many times? N times. That's what I have written here. I have got n vertices and degree of each vertex is 3. So left hand is n into 3. That is equal to 2 times the number of edges. And number of edges is given by 9. So it is 3n is equal to 9 2s are 18. Therefore n is equal to 3 6 are Therefore n is equal to 6. So which means if I consider this graph G with 9 edges and with the degree of all the vertices 3, definitely in that graph you can note that the number of vertices must be 6. And second example, and I just need to do the same thing again. G has 10 edges. So they are saying that the number of edges is equal to 10, and they are saying 2 vertices of degree 4. So they are saying that degree of V1 is 4 and degree of V2 is also 4. And from degree of V3, degree of V4 and so on, degree of Vn, that is equal to 3. Okay, so only the degree of 2 vertices is 4 and for the degree of remaining vertices is equal to 3. So by using handshaking property, summation I is equal to 1 to n, degree of Vi is equal to 2 times the number of edges. So this can be rewritten as what? We have got 2 vertices. Okay, we have got 2 vertices of degree 4 plus how many vertices are remaining now? Out of n vertices, 2 vertices are taken off. So n minus 2 vertices are remaining. Degree of each of this vertex is what? 3. It is equal to, so 2 times the number of edges, that is 2 into 10. That's equal to 20. So 2 4s are 8 plus 3n minus 2 3s are 6 is equal to 20. 8 minus 6 is equal to 2. Take that 2 to the other side, it becomes 18. Therefore n is equal to 6. Even for this example, the number of vertices is exactly equal to 6. In the final case, so they are saying that G is regular with 15 edges, which means they are saying that so E is equal to 15, number of edges is 15, and they said degree of the graph is a regular graph. So regular graph means what? So degree of each vertex is equal to what? K. Okay, degree of each vertex is same, and I don't know the degree of this. So they just said that it's a regular graph. Regular graph means degree of every vertex should be common. It should be same. So now if I consider the handshaking property, summation degree of V for V belongs to V, summation I is equal to 1, I equal to 1 to n, degree of Vi is equal to 2 times the number of edges. So we said that we have got n vertices and degree of each vertex is k. So that is equal to 2 times the number of edges. We are not interested in finding k, we are interested in finding the value of n itself. Okay, now 2 times the number of edges, that is 2 into 15. So that is 30. So it says the value of k is equal to what? 30 by n. Now the question is, what is k? K is degree. So degree cannot be a fraction. Degree is always an integer, that a positive integer. N is also positive integer. Now the question is, what should be the value of n for which the value of k remains integer? You can take n is equal to 1, n equal to 2, n equal to 3, 4 is not dividing this number, 5 divides, 6 divides, 7 is not dividing, 8, 9, 10 divides this number, 11, 12, 13, 14, 15 divides this number, and 30 divides this number. Okay, so which means if you consider any k regular graph with 15 edges, you can have these possibilities. You can have only one vertex in that graph, or you can have only 2 vertices, only 3 vertices, or only 5 vertices, 6 vertices, 10 vertices, or 15 vertices, or you can have 30 vertices. Graph with 30 vertices and 15 edges. Just draw and try this. Any doubts in this? Okay, so that's good. So no doubts. Let me just try the next example. So next example is quite similar, but in this example the expectation is different. So the question is, does there exist a cubic graph with 11 vertices? And second question is, does there exist a four regular graph with first case 15 edges and second case 10 edges? Okay, so even this uses handshaking property, nothing more than that. If we just check out, does there exist a cubic graph with 11 vertices? So they have given the number of vertices here. Let's coordinate f v equal to 11. And further, what we know here is its n value is 11. And further, we know that it's a cubic graph. For cubic graph, degree of each vertex is what? 3. For every v belongs to the vertex set. Now consider the handshaking property. Sum of the degrees of all the vertices is equal to 2 times the number of edges. And they have not given how many edges are present in this graph. Let me just check out. So with this, can we just check any possibilities we have here? So we have got 11 vertices and degree of each vertex is what? 3. That's equal to 2 times number of edges. It is saying that number of edges is equal to 33 by 2. Is it possible to have, so 33 by 2, so is it possible to have these many edges? No, because it is not an integer. We know that number of vertices, number of edges, degree cannot be a fraction. It is always an integer, which means that since it is not an integer, it is not possible to have. So not possible to have this graph. Not possible to have this graph. Simple. In the handshaking property, we just checked that we found the number of edges. In this case, because we were knowing everything except the number of edges, we just tried to find that, and we ended with what is number of edges is a fraction, which is not possible. So that should be an integer always. So therefore, it is not possible to have this graph. Second case. So they are saying that degree of each vertex is 4. Number of vertices is n. We don't know this. Okay, but we know degree of each vertex is 4. So for all v belongs to 3. And for the case number A, for the first case, number of edges is 15. Number of edges is equal to 15. So consider the handshaking property. Sum of the degrees of all the vertices is equal to 2 times number of edges. We have got n vertices, degree of each vertex is 4, which is equal to 2 into 15. So 4n is equal to 15 2s are 30. N is equal to what? 30 by 4. It is once again not an integer. Okay, it is not an integer. We just need to find this number of vertices. It's not an integer, so not possible to have this graph. Okay, this graph is not possible. And second possibility is number of edges is given by 10. Now, if number of edges is 10, so in the same handshaking property, we can note that, so we have got n vertices, degree of each vertex is 4, which is equal to 2 times the number of edges is 10. So it is 4n is equal to 20, therefore n is equal to 5. So which means that we can definitely have, so therefore we can have with this data we can definitely construct the graph. So what we are saying here, so here with the degree of each vertex is 4, we can draw this graph, and actually we already constructed this graph. I think n is equal to 5 and degree of each vertex is 4. I think I drawn this, no, and here this is this. Okay, I can just pick up this. I will just show you how does it looks. Let me consider this. So just to show you people, it is not, you need not write it in the exam. You're not writing it. Just to show you people how this graph looks. Doing this. Four, 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 four. So this is the graph we are talking here. So okay, so we are actually talking about this. It's a 4 regular graph with 5 vertices and how many edges? 10 edges. So outside 5 edges and inside another 5 edges are there. So totally 10 edges are present on this graph. Okay, so these 2 questions are very important. Along with that, we have one more question on degree. Let me just take up that. Yes, this is that graph. This is the problem. Okay, so for a graph, G is equal to V comma E, what is the largest possible value of value of V if number of edges is equal to 19 and degree of each vertex is greater than or equal to 4. Okay, degree of each vertex is greater than or equal to 4. Okay, let me just check out this. So number of edges they have given it as 19, number of vertices is equal to n, and degree of each vertex they're saying it is 4 for all V belongs to the vertex set. So as usual, just take the help of the handshaking property. Sum of the degrees of all the vertices is always equal to what? 2 times the number of edges. Okay, it is, and we know that. So degree of each vertex is greater than or equal to 4 means what? 4 less than or equal to degree of V, which means we have got n vertices, degree of each vertex is 4, which is less than or equal to 2 times the number of edges. Okay, this number is less than or equal to the number of vertices into 4, because 4 is less than or equal to 1, that is degree of each vertex is greater than or equal to 4. So which means n becomes what? N is less than or equal to, so 19 by 2, which is approximately equal to what? 9.5. And we know that number of vertices cannot be a fraction or cannot be a some real number, arbitrary real number. It should be an integer. So which means that, so at the max what? 9.5, which means what is the greatest integer which is less than or equal to 9.5, which is 9. Therefore the value of n is equal to 9. Okay, so with respect to this data, so what is the largest possible value? What is the largest possible integer which is less than or equal to 9.5 is 9. So we are expecting these many vertices are present in my graph. To have this graph, this many vertices should present. Okay, along with this, one more result is there, and this is very often asked. And this question is, so you can note that this is the first time you are seeing so many problems under this graph theory. So that's what you have got more problems and theorems on a vertex degree, and obviously you can expect questions. So from you. So important theorem again, and about three problems whatever I discussed, all the three are very important. Okay, now for a graph, it's a very simple result again. For a graph with n vertices and m edges, if delta is the minimum and this capital delta is the maximum, is the maximum of the degrees of vertices, show that delta less than or equal to 2m by n less than or equal to capital delta. It's the simplest result which uses handshaking property again. Let me assume that the number of vertices here is n. I need not to mention, assume it is given here. Number of vertices is n and number of edges is equal to m. Okay, so now let me assume that degree of v1 is d1, degree of v2 is d2, degree of v3 is d3, and so on. Degree of vn is dn. Okay, and what they are telling here, among these degrees, the small delta is the minimum. Okay, so the small delta represents the minimum value, that is one of this is carrying this delta value and that is the least value among this, and this capital delta is carrying the maximum value. So instead of least and greatest, they are using minimum and maximum. People know the difference between least and minimum. You can have more than one minimum, more than one maximum, and least and greatest is always unique. That's why they are not using that word. Okay, so accordingly, what happens here? We know that delta is smallest, which means that this delta is less than or equal to d1 for sure. This degree, delta is representing one particular number, and that is matching with any one of this. I don't know which is that degree is. That's why I will just go with delta is less than or equal to d1. Delta is also less than or equal to d2. Delta is less than or equal to d3, and so on. Delta less than or is equal to dn. Now let me just add all this. If I just take the sum of this, that will give us delta plus delta plus delta plus and so on, delta less than or equal to d1 plus d2 plus d3 and so on plus dn. Okay, what this is happening here, you are multiplying delta to itself how many times? N times. You have got n vertices into delta, that is less than or is equal to sum of the degrees. You can note that this is sum of the degrees of all the vertices. I is equal to 1 to n, di is there. This is nothing but your left hand side of the handshaking property, that is the sum of the degrees of all the vertices. That should be always equal to what? This is always equal to 2m by using what? Handshaking property. Handshaking property. So we are saying that n delta less than or is equal to 2m. So which means delta is less than or equal to what? 2m by n. Let me call it as result number 1. And similarly, what they have said here is capital delta is the maximum among this n degrees, which means d1 should be less than or equal to capital delta, d2 should be less than or equal to capital delta, and so on. dn should be less than or equal to capital delta. Now I'll just do the same thing again. I'll just take the summation of this. So d1 plus d2 plus d3 plus and so on plus dn less than or is equal to, you're adding delta to itself n times, so it becomes n delta. And the left hand side gives us what? By handshaking property, this is 2 times the number of edges, that is 2m. less than or equal to n delta from handshaking property again. So now this is nothing but 2m by n less than or equal to capital delta. This is my result number 2. We are saying from 1 and 2, we are saying that delta, small delta is less than or equal to 2m by n, but that number is less than or equal to capital delta. So hence this result holds good. And as I mentioned, this problem is very important. If you just learn these 4 problems another Saturday, that will be enough. Okay, you just find some more problems in the notes. If you get some time, just go through them. Otherwise, these 4 problems will work for you. Okay, so this completes the vertex degree part. If you have any doubts, we can discuss that. Very important part. So as I mentioned, under vertex degree, what all you need to know. So one is, they may ask you to verify the handshaking property. They may ask you to identify the isolated vertex, pendant edge. Afterwards, they may ask you to prove this result, and based on that, they may ask you to determine whether the graphs with this following degree sequence possible or not. And definition of regular graph is very important, and they can ask you to any of these 4 problems. So next one is isomorphism. Okay, which part you want? Okay. Any doubts in this? Yeah. Okay. So isomorphism means the name is the name is telling like okay. So by looking at the name, so I don't know what you people are thinking about this, but it just speaks about only this. Okay, let me just consider this to example itself. Okay, A protects A, protects B, protects C, protects D. A, B, C and D. Isomorphism just says that shape of the graph is not the important. The information what graph carries important. So these 2 graphs are given in different shapes, but they are carrying the same information. So these 2 graphs are same. Isomorphism just says this. Okay, so by looking at the shape of the graph, you should not decide the 2 graphs are different. So you should identify what the information these 2 graphs are carrying. If they are carrying the same information, those 2 graphs are same. That is what the isomorphism says. In this case, you can note that A and B are adjacent, A and B are adjacent. A and C are non-adjacent, A and C are non-adjacent. So D and B are non-adjacent, D and B are non-adjacent. That's all. So these 2 graphs seems to be different because of their shapes. It looks like a circle and it looks like a square. But they're actually carrying the same information, so these 2 graphs are identical. That is what the isomorphism says. And when we have got simple shapes like this, it's quite easy for us to identify like whether they are same or different. But when we have got any huge information, when these graphs becomes bigger, like so more number of edges and more number of vertices, it will be a tough job for us to identify the difference. In those cases, we will take the help of the definition. And this is what the definition says. Just push it to that side. Okay, so this is what they may ask you to, they can ask you to define graph isomorphism, and then they can ask you to determine whether the following graphs are isomorphic or not. The question will be like this, so please learn this definition as well. This is what the definition says. Let G1 is equal to V1 comma E1 and G2 is equal to V2 comma E2. I have two graphs. So now you define a function. If I can find a function f from vertex set V1 to vertex set V2, vertex set of this to vertex set of the second graph is called, this function is called graph isomorphism. Graph isomorphism if, first of all, f is one-to-one correspondence. Try to understand this. F is one-to-one correspondence. What do you mean by this? F is bijective. You are saying f is a bijective function. That is, there is a one-to-one mapping between the vertices of these two graphs. So A is mapped to A. Like if I just give a different name to it, instead of ABCD, since I just named it as ABCD, instead of this, if I just do this, it's my U, this is V, W, X. So what I'm doing here, I'm defining my function f in such a way that, so f of A is equal to U, f of B is equal to V, f of C is equal to W, f of D is equal to X. Okay, I'm just defining the function f from the vertex set V1 to vertex set V2 in such a way that, so that becomes what? One-to-one mapping. It's a bijective mapping. One-to-one correspondence means it's a bijective mapping. Okay, it's a bijective mapping. So this is the first condition it needs to satisfy. And condition number 2 is, along with this is what we're expecting. From AB belongs to V1, A comma B belongs to E1. For all AB belongs to V1, A comma B belongs to E1 should imply f of A comma f of B belongs to E2. So it actually speaks about that. So this is nothing but, this is called vertex adjacency is preserved. This means vertex adjacency is preserved. What do you mean by this? Okay, so this is just saying this. Suppose in this example, if I interchange this position of this U and V, see what happens. If this is my V and this is my U. Okay, now in this graph, A and B are adjacent. Okay, A and B are adjacent. Their mapping is what? Their images are U and V. Okay, so in this case it is not becoming an issue. Okay, X and U. Okay, X, C and D, X and U. In this case what happened? W. So f of C is W and f of D is X. Instead of U, okay, instead of interchanging these two, E and B are adjacent, E and C. I should make E and C adjacent. Here I should make A and C adjacent. A and C mapping are U and W. So U and W. Okay, yes, that is what you can see here. You can note that A and C are non-adjacent vertices. So there is no edge between these two vertices. But look at these two. U and W are adjacent vertices. U and W. A and C are non-adjacent, but their images U and W are adjacent vertices. So this cannot be. So though there is a one-to-one mapping, so the mapping whatever I got is absolutely fine. There is a one-to-one mapping between these vertices to these vertices. But the information what these two in graphs are carrying is different. Because of what? Because of the wrong mapping whatever I did here. What is the wrong mapping that I did here? So initially the first mapping whatever I did was absolutely fine. So now what happened here, I just changed a bit here. Accordingly what happened, so A and C are non-adjacent here, whereas their images, so image of A is U, image of C is W, but U and W are adjacent here. So if these two are non-adjacent, we're expecting even these images are also non-adjacent. If A and D are adjacent, so image of A is U, image of D is X, U and X should be adjacent, but U and X are non-adjacent here. Okay, if the two vertices are adjacent in the first graph, we're expecting their images are also adjacent in the second graph. Okay, so if I can find the one-to-one mapping, along with that, preserving the vertex adjacency is very important. Please keep this in mind when you are defining. So you should take care of the vertex adjacency. If these two things are taken care, so then we say that the two graphs are isomorphic. That is, here we say G1 is isomorphic to G2, and this is what the symbol we use to say G1 and G2 are isomorphic. What do you mean by that? G1 and G2 are given in two different shapes, but they are carrying the same information. Now accordingly what I am supposed to do now here, so here image of A is, okay, A is there here, so image of A is X. Suppose if I keep image of A as X here, and image of B is what? V, and image of C is U, and image of D is W. And if I change it accordingly, in this case you can note that, so this mapping is absolutely fine. Image of A becomes what? X. Okay, if I change it accordingly now, so though the two graphs are isomorphic here, if I am not mapping them properly, so though we have the one-to-one correspondence, exists between those two graphs, this vertex adjacency is not preserved. In that case, though the two graphs are isomorphic, we failed in proving that. So that is why you need to take care of the vertex adjacency as well. So now what I will do, I will map A to X, I will map B to what? V, I will map C to U, and D to W. So now you can note that if A and B are adjacent here, their images are also adjacent. If A and C are non-adjacent here, A and C are non-adjacent, X and U are also non-adjacent. Okay, so if you can prove this, you are proving that the two graphs are carrying the same information, though they are given in different shapes. Okay, now how do you do this? Okay, just to show you people how it works, I just showed you here. Now I will explain you how you are supposed to prove it in the exam. Okay, so how you are supposed to prove the same result in the exam. Let me just take up that. To do that, let me consider the same example. Instead of taking a different one, let me consider the same example. As I mentioned, definition is very important here. So the question will be like this: determine whether the following graphs are isomorphic. So normally if you just check out the previous year question papers and model paper, every question paper should carry problem on isomorphism, but don't take chances. So just by reading graph isomorphism, don't leave the other topics. So we cannot take such chances because we have got too much of syllabus and limited option. So definitely there is a scope for rotation. That's why please don't take chances. Okay, this is my graph G1, and let me call this one as graph G2. Okay, so now how you should prove the result, I am showing you that. So first you people please do this. First check whether you have got same number of vertices. So 1, 2, 3, 4, same number of vertices. Okay, if you have got same number of vertices, only in that case isomorphism possible. Please keep that in mind. One-to-one correspondence is possible only when the number of vertices in the first graph and second graph are same. First thing is done. Second thing is, So do we have same number of edges? Yes, it is true. 1, 2, 3, 4. 1, 2, 3, 4. 4 edges, 4 edges. And third thing we need to check is, do we have the same degree or what? Okay, check degree. Both are, and you can note that both are two regular graphs here. Two regular graphs. What do you mean by that? Degree of each vertex is true in both the graphs. Okay. Now, if these three conditions are satisfied, only in that case you proceed further to show these two graphs are isomorphic. If these three conditions, if any one of the conditions failed, in that case directly you are saying that the two graphs are not isomorphic. Finished. Now, how do you show this? So for this, first thing what you should do is define f from v1 to v2 by, what I'm doing here, let me just define v1 first. v1 is given by what? A, B, C and D. So vertex at v2 is given by what? X, V, U, W. Order is not important, so you can just put it in any order. So f is a function from v1 to v2 by, how I am supposed to define this? So this, if the number of vertices are same, we can easily define it by f of a is equal to x. Please take care of the vertex adjacency. When you are defining this, you should define it in such a way that a vertex adjacency is preserved. F of a is x, f of b is v. Next, f of c is u, and f of d is w. Or you can clearly note that f is one-to-one correspondence. How do you know this? Every element of A has unique images and every element of V2 has unique 2 images. That's enough. So f is one-to-one correspondence. You need not to prove it. So it is we already know. So if it is one-to-one and onto function, it's both one-to-one and onto. So it is definitely a bijective function. That's what I've written. F is one-to-one correspondence. So the first part of the definition is done. Okay, this condition is proved. The second condition I need to prove now. So what I will do now, I will just consider here. Here we can note that. Vertex adjacency is preserved. Vertex adjacency is preserved. Okay, how do you show this? What I am supposed to do here, I should prove few vertices like, so AB, this edge is mapped to what? AB is mapped to XV. AB is mapped to XV. Okay, next. I got only four edges here. Let me just list all the 4 edges and we will just write the corresponding edges in the second graph. So AB, BC. Next we have CD, DA. CD, DA. Okay, this edge is mapped to what? Image of B is V. Image of C is U. Image of C is U. Image of D is W. It's W, and image of A is X. So therefore G1 is isomorphic to G2. That's all. It is so simple. What you should check first, same number of vertices, same number of edges, and just check out the degree sequence. If the degree sequence also matches, then proceed further. Write V1, V2. Now define the function f from V1 to V2 in such a way that it becomes one-to-one correspondence. And when you are defining it, you should take care of the vertex adjacency as well, so that you can just write them blindly. You need not to go back to the graph to check that. So you will just write all the edges from the first graph. You can write the corresponding edges in the second graph. So you are showing the vertex adjacency is preserved and the graphs are isomorphic. Okay. Next, let me just check out the remaining possibilities. Any doubts in this? Okay. Let me just consider this example now. This is A, B, C, D. This is M, N, P, Q. This is my graph G1 and this is the graph G2. So what about in this example? So are they isomorphic? No. So you can note that the number of vertices matched. So A, B, C, D, M, N, P, Q. So and you can different one-to-one correspondence. F of A is M, F of B is N, F of C is P, F of D is Q. That can be done. But if you just count the number of edges, it is not matching. So number of edges are not matching, hence the two graphs are not isomorphic. Okay, number of edges are not same. So G1 is not isomorphic to G2. I need not to prove anything here. Live. Finished. Third case. So okay, you saw this one situation. Now have a look at this situation now. Here A, B, C, D, P, Q, R, S. This is my G1. This is G2. Are they same? So what is the next question? So we can note that same number of vertices 1, 2, 3, 4, 1, 2, 3, 4. Same number of edges 1, 2, 3, 1, 2, 3. But still they are not isomorphic. They are not carrying the same information. How we will decide that? Here we can note that in G1 we have degree of A is equal to what? 3. But we do not have vertex with degree 3 in G2. It's enough for us. There's one reason is enough for us to say these two are not isomorphic. But is this the only reason that we can give here? No, we can give some more reasons. Which are those reasons? We can find 3 vertices of degree 1. Degree 1, degree 1, degree 1. But we can find only 2 vertices of degree 1 in the second graph. This is one more reason you can give. We can find no vertices of degree 2 in this first graph. But we can find 2 vertices of degree 2 in the second graph. And we can find D is adjacent to the vertex whose degree is 3. But we cannot find a vertex whose vertex which is vertex with the degree 3 which is adjacent to a vertex of degree 3. That's one more reason. Like this you can give so many reasons to conclude. So degree of the vertex, to conclude the two graphs are not isomorphic. You're just saying that. So these two are carrying two different information. So though number of edges and number of vertices are same, so the information what these two are carrying are not same. Now look at this situation. Third one, let me just try the fourth case and look at this situation. In this case, degree sequence did not match. So degree sequence like that, you can just put it like this. So degree sequence of this one is what? 3, 1, 1. In this case, degree sequence is what? 1, 2, 2, 1. Degree sequence are not matching. Now have a look at this example. A, B, C, D, E, F. This is A, this is B, this is C, this is D, E, F. Look at the degree sequence. It's 1, this is also 1, and this one is with 3, this one is with 2, and for this one it is 1. Look at this one. It's 1, 2 for this, 3 for this, 1, 2, 3, and 2 for this, and 1 for this, and 1 for this. 1, 2, 3. 3 vertices of degree 1, 1, 2, 3. 3 vertices of degree 1. So 2 vertices of degree 2, 2 vertices of degree 2. 3 vertices of degree, 1 vertex of degree 3, 1 vertex of degree 3. Even degree sequence matched. Same number of vertices, same number of edges. Degree sequence is also matching, but still these two graphs are not isomorphic. Why? So here this is what I was telling you people. Even in this case you can define one-to-one correspondence, like f of A is mapped to A, f of B mapped to B, f of C mapped to C, D, E, F, like this. That gives us one-to-one correspondence, but vertex adjacency is not preserved. How? Here you can note that C is one vertex with a degree what? 3, which is adjacent to a vertex of degree, which is adjacent to one vertex of degree 1. Whereas C is the only vertex in this graph whose degree is 3, which is adjacent to two vertices of degree 1. Okay. In G, okay, this is G1. G2. In G1, we have vertex C, whose degree is 3 and is adjacent to two vertices of degree 1, but we cannot find vertex with same information in G2. This one reason is enough. This is one vertex with the degree 3. Here C is the only vertex with the degree 3. This is adjacent to two vertices of degree 1, whereas this is adjacent to only one vertex of degree 1. And this is adjacent to two vertices of degree 2, whereas this is adjacent to only one vertex of degree 2. Okay, so like this you can give your own reasons. You can just give your reasons here. Though the degree sequence is matched, it's not enough. You should keep that in mind. So matching degree sequence is not enough for us. So we should not be in a position to find at least one set. So at least one information is mismatching here. Okay, so that's what I said here. So C is one vertex with the degree 3, which is adjacent to two vertices of degree 1, and that information is not, we can't find that information in G2. Therefore, clearly G1 is not isomorphic to G2. Okay, so if I just consider the first example, in this example everything matches. Degree sequence matches, and you can note that since it's a two regular graph, and we need not to worry about that one as well, because these two are exactly carrying the same information there. Okay, next example. I'll just take up one more example, and with this we'll wind up this. We'll find some more problems in the notes. You can just try them. Actually, these are bipartite graphs. Just check out carefully. You can show them as bipartite graphs. This is my G1, this is G2. Okay, so this is what the given problem is. Problem number 5. This is given here, and we need to show whether they are isomorphic or not. So first point. So same number of vertices. These are the vertices here, and there is no vertex at this point. Six vertices here, same number of edges, and both are three regular graphs. Okay, so now let me just label them first. So here labeling is not given. If the labeling is given, we can just make use of it. If the labeling is not given, we need to label it. If the labeling is not given, it will be easy for us to manage, because we can just label in such a way that the things become simple for us. Okay, so G1. So what I will do now, I will just map this one as this is my V1, this is V2, V3, V4, V5, V6. Now I need to label this graph. Okay, let me label the graphs. So as I mentioned already, when you are labeling the graph, you should take care of the vertex adjacency. Be careful with that. Okay, now V1. I will because since both are three regular graphs, I can start from any vertex. There is no restriction like I should start from here or start from here. No, you can start from any vertex. Okay, let me just start from this vertex itself, or you can start from here. You can just start with any arbitrary vertex. I will just start with this itself. Let me assume this is my V1 dash. V1 dash is what? Image of V1. Okay, that is what I will keep in my mind when I am defining the function. So since just to make the labeling part simple, I'm just going with a dash instead of using different symbols. V1 dash, and V1 is adjacent to what? V2. I will do that first. V2, so it is V2 dash, and V2 dash is adjacent to what? V4. So V2 dash is adjacent to V4. Let me call it as V4 dash, and V4 dash is adjacent to what? V3. So V4 dash is adjacent to V3. I just write it. Okay, we can mark it here itself, but yeah, V3 dash. And now when I'm doing this, I need to take care of the other part as well. So V3 dash is adjacent to V1 dash. Is it true? Yes, V3 dash is adjacent to V1 dash. Yeah, that's good, but it's not an issue then. And V3 dash, V3 goes to what? V5. So V3 is adjacent to V5, right? V5 dash. Is that fine? So V5, it is adjacent to V3 and V2. V5 is adjacent to V3 and V2. Yes, even that part is taken care. Okay. Next is what? V5 is adjacent to V6. V5 dash is adjacent to V6 dash. Now the question is this V6 dash is adjacent to these three vertices? V6 to V1, okay. V6 to V4, that is also there, and V6 to V5. Yes. I just labeled this in such a way that I took care. I've taken care of the vertex adjacency, so that the labeling part becomes simple. That is the defining your one-to-one correspondence becomes simple. You should not label the second graph arbitrarily. Please be careful with this. Don't label the second graph arbitrarily. When you are labeling the graph, you should take care of what? Vertex adjacency. And if you are using primes here like this, then even that makes things simple for us when we are defining the function. Now let us define. Now define f from v1 to v2. Okay, so v1 is what? So v1 is equal to v1, v2, v3, v4, v5, v6, and v2 contains v1 dash, v2 dash, v3 dash, v4 dash, v5 dash, v6 dash, and I have just labeled this in such a way that I can define the function like this: f of vi is equal to vi dash for I lying between 1 and 6. So f of v1 is v1 dash, f of v2 is v2 dash, f of v3 is v3 dash, like that. F of v6 becomes what? v6 dash. That's what I've written here, and it represents one-to-one correspondence. It is one-to-one correspondence. That part is done. Second part is what, as I mentioned, we will just show the labeling part. Okay, how many edges are there here? 6. Total 9 edges are there. Let me write all those 9 edges here first. So v1, v2, v1, v3, v1, v6, and I will just show its mapping afterwards. Let me just write those edges first. So v4, v2, v4, v3, v4, v6, and final list is v5, v2, v5, v3, v5, v6. And we know that we have labeled this in such a way that v1 goes to v1 dash, so it is v1 dash, v2 dash, and v1 goes to v1 dash, v3 goes to v3 dash. So v1 dash, v6 dash, and this is v4 dash, v2 dash, I'm sorry, v2 dash, v4 dash, v3 dash, v4 dash, v6 dash, v5 dash, v2 dash, and v5 dash, v3 dash, v5 dash, v6 dash. So therefore vertex adjacency is preserved. That is, vertex adjacency is preserved. So therefore G1 is isomorphic to G2. That's all. Okay, if you have got two possibilities here, there is a chance that F is not isomorphic, either because of number of vertices or because of number of edges, or it may be because of the degree sequence. Sometimes though the degree sequence is matching, so the information what they are carrying is different. So if all these cases are, if any of these four cases comes, you can say the two graphs are not isomorphic. If you can't show that, so in those cases we'll be labeling the graph, and you should label the graph and define your isomorphism or define your function in such a way that the function becomes one-to-one correspondence and the vertex adjacency is preserved. And for this example, this is what you should write for 6 to 7 marks. If you have any doubts, we can discuss that. Okay, so for more problems you can just refer to the notes. Okay, I'll send you the notes as well, and for more problems you can refer to the notes. And I just need to discuss one more result, one more definition, that is Euler circuit, so Euler trail and Euler circuit. Okay, if, first of all, to talk about Euler trail or Euler circuit, the basic expectation is the graph G should be. So G should be a connected graph. Should be connected graph. It can be a multi-graph as well. So, but it should be a connected graph. If it's a connected graph, we say that so graph G has Euler circuit. So we say G has Euler circuit. Sorry. We say G has Euler circuit if there is a circuit in G. There is a circuit in G which traverses every edge of the graph. Every edge of the graph exactly once. That's all. That is, you should find a circuit. Circuit means there should not be a repetition of edge. You can have the repetition of vertex. It's a closed walk. There is no repetition of vertices. You can have there is no repetition of edges. You can have the repetition of vertices. But what is the expectation is that circuit should traverse through what? Every edge exactly once. And further, if there is an open trail, and the graph is called Euler graph actually, and if there is an open trail, I need not to mention open trail, I can just say just trail itself is open trail from A to B, open trail from A to B in G, that traverses every edge in G exactly once. The trail is called Euler trail. So, okay, what is the expectation here? You have some graph. Okay, so there is no Euler trail in this. So 1, 2, 3, 4. Okay, there is no Euler trail in this. Let you leave it. Okay. Now let me consider this example and I'll explain you what we're exactly talking about. Okay, and this is the most common question on this. Find an Euler trail. Find an Euler circuit first. Find an Euler circuit for the following graph. This is the first question, and second question is, if the edge D comma E is deleted, this D comma E is removed from this graph, find an Euler trail. Find an Euler trail for the resulting graph, for the resulting subgraph. Actually, it is no way connected to isomorphism. It's actually a problem on a trail and circuit. And this is what the question is. This is what the given graph. Okay, let me label them. It is A, B, C, D, E, F, G, K, H, I, J, K. Okay, so this is what the given graph is. So I should find the Euler circuit. What is the meaning of finding an Euler circuit? I can start from any vertex. I should end up with the same vertex. But when I'm reaching this vertex here back, I should have traversed through all the edges which are present here. But how many times? Exactly once. So otherwise it won't be a circuit at all. And the second part of the question is what? I should find Euler trail of subgraph which is obtained by deleting this edge. Okay. So first let me find the Euler circuit. Okay, what I will do now, I will start from D itself. D, so D, so I'm using this, I'm just moving on this one directly first. Okay, so D2, E. Next, I can just move on any of the sets because none of the edges are used here. Okay, if I just go up, E to B, B to C, and this is not the only way. You can just choose your own way. But the only thing is you're supposed to move on all the edges of the graph exactly once. That's why I'm just marking them so that I'm not supposed to move on those edges again. So I just went like this. So when I reach this point, there is no option. I have to go down. Okay, C to G. Okay, and G to K. Okay, and then I will just go to, from K there is no option. I have to go to J. So J to, okay, I will go to G. G back. You can just reach the same vertex again, but you cannot just move on the same edge again. Okay, so no option. I have to go like this, G to B, and I will just go like this. I should end up with D now. Okay, so I just reached B, so we'll go to A to D, okay, D to H, H to I, okay, H to I. Now from I can move like this, or I can move like this, or I can go like this. Which one? Let me just go. Okay, let me just go in this way. I to J. So now J to F. Now F to I. Now I to E. Now E to F. Okay. Next, this is used. Now F to B. Now B to D. Started with D, ended with D, and we can note that we moved on all the vertices, all the edges exactly once. So this graph is called Euler graph, and the circuit which is obtained here is called the Euler circuit. And second part of the graph is what? Second problem is what? So let's copy this. I should consider for the second problem this FBD, that's right. Yeah, so in this graph what I'm supposed to do, I need to delete this edge. and I should find the islet trail between what? D and E. Islet trail between D and E, which traverses through all the edges exactly once. For that, what I will do, I already have the answer here. That's what. So I just found this answer in such a way that I did not start with an arbitrary vertex. I just had the intention of finding the answer for the second question as well. What I did here, I started with this such a way that I'm just moving on this DE. If I just remove this, okay, note that this edge end, it started with E, ended with the D. So this is an example. This is the answer for the second question. If you want, I can just try that. So E to B, B to C, G, K, J, G, B, A, okay, B, A, D, H, I, J, F, I, E, F, B, D. So this becomes islet trail because it just covered all the edges exactly once, and we ended with the we ended with D, started with E and ended with D. So this will give us ED trail and DE trail. So both are fine. So these are all what? These are not the direct edges. These are all undirected edges. So whether you are starting from E or starting from D doesn't make any difference. This whatever you have written here, this represents both ED trail as well as DE trail. Friends, any doubts in this? But I'll give you just one note here. So to have either circuit, to have either circuit, to have either circuit in G, or to have circuits in G, G should be free from, vertices with odd degree. Okay, so first point. And second point, to have islet trail in G, G should have exactly two vertices of odd degree. So what we are expecting here, to have the islet circuit, degree of each vertex should be even. You can just see 2, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4. Like that, you can note the degree of each vertex is even in this case. So you can have the islet circuit. In this example, you will find only two vertices. D and E are the only two vertices whose degree is odd. So then we can definitely have islet trail in this case between D and E. And in this case, you can have the Euler circuit starting from any vertex. I started with D here, right? You need not start from D. You can start from I, you can start from J, you can start from any vertex. You can end with the same vertex by moving through all the edges exactly once. Okay? The basic expectation is what? So every degree of every vertex should be even, so that you can have Euler circuit. If you have exactly two vertices of odd degree, you can have the islet trail in that case. Okay, it's enough. This is what the syllabus you have from graph theory, and as I mentioned, so concentrate on all the definitions. So every definition counts, every definition is important here, and problems on vertex degree and the vertex degree concept and isomorphism concept are very, very important. There is a chance that in the question paper you may get problems only from isomorphism and vertex theory. You can find even the questions papers of that kind. And one problem, most of the time, as I mentioned, you can definitely expect one subdivision dedicated only on definitions on graph theory. So that is why, so make sure that you are going through all the definition and the concepts which I explained. So by keeping these definitions and these concepts in your mind, or you can read, I will just post it in the Google Classroom. Post this whatever I wrote here, I will post it in the Google Classroom. I will post even the notes on graph theory. It will go through it, and if you get any doubts, you can always talk to me. That's one thing. And one more point is, keep the whatever I explained in the class in your mind. By keeping this as main track, so whatever you want, you just go back to that notes and just take those concepts and come back and do it here. And definitely your notes, the notes which I'm posting will be having more information. If you get some time, if you get time to go through all the things, it's always good. People do that. Otherwise, so take the problem and concept from here, go there, take the necessary information from that notes, just come back. So just to do this. Okay, if anybody has doubts, we can discuss. Otherwise, we can stop the class here.